Okay, let's watch the merry-go-round, activity 1 of the lab. So notice where it's starting at x equals 1.25, y equals 0, so that gives us the radius. And if I run the thing, it seems to go smoothly. What do you think? Is it constant? Doesn't seem to be slowing down or speeding up, so we can, by taking measurements, we can determine whether that's true or not, but it seems to be going at a constant rate. And notice it stops after 2.5 seconds. And if you pay attention to the x and y coordinates, look at them. They're the same value, the same magnitude. So that from that we can get the exact angle. And if we know the exact angle, we can get the exact number of rotations and the exact number of radians. Divide by 2.5 seconds, and that will give us the rate at which it's spinning, if in fact it's spinning at a constant speed. Okay, I reset it, and I've been stepping it one at a time to try and get it. And I'm trying to get it to 45 degrees. Watch what happens. Watch the x and y's. So it's 9:11, 8:56. And then it went past, so I can't really get it exactly 45 degrees, but that's pretty close right now. But let me, whoops. And seeing the same thing at 180 degrees, or a half a rotation, or pi radians, you see that the x isn't quite 1.25 and the y is positive. And if I press this button one more time, the y goes negative. So we have the same thing here. We can't land exactly on the place of a half a rotation. Okay, skipping ahead to the next simulation and the third problem. The first two are on that first simulation. Let's just run this and see. We have a turntable again with a quarter and penny on it. And if we just run it, yeah, it looks like it's turning at a steady rate. So does that mean no angular acceleration? It means the angular velocity is most likely constant. We can check that to see. Doesn't seem to be speeding up or slowing down. It's going. And so it went 8 seconds. I didn't count the number of rotations, but it went back to where it started. It started at that 45-degree angle, and so it's back there. So if in fact it's constant, we could just measure the number of rotations and divide by the time and get the rotations per second, or turn the rotations into radians and get the radians per second. And what's worth noticing here and different is that every time the turntable goes once, the penny goes once, and the quarter goes once. So their rotational speed, the number of radians or rotations or degrees per second is going to be the same, but their linear speed, the speed at which they're actually moving, this is going to be slower, right? Because it covers less distance. And so the way it works is if the radius is twice as big, then the circumference of the circle will be twice as big, and the speed, or what we call tangential velocity, the vt, will be twice as big. And if this is half the radius, this is going to be half as far in the same amount of time, so half the angle of velocity. And the same would be true of the acceleration if they were accelerating, but in this case, they're not. Okay, here's number 4. Another merry-go-round, but notice the radius is different. Let's just run this. Same deal, right? A red dot. It's giving us the x and y positions. It seems to be slowing down. Definitely slowing down. Slower, slower, slower. Slower, yeah, okay. So 3.96 seconds. It appears to have come from a stop. So it didn't start at a stop. It was moving in the beginning, just that the video started, and it slowed down. So it looks like we have a negative acceleration here. And so the velocity, that means, is going to be different at every instant. The final velocity is 0. We're going to have to get the initial. But remember, if we take the one rotation, 2 pi radians, and divide it by 3.96, what are we going to get? We're going to get the average angular velocity, and that's not going to be what the initial was. So if you remember, if it starts at 0, it must have been going faster. So those equations and that idea about average and instantaneous velocity are what are important in this problem. Another way of thinking about this, or just pay attention to, if it's slowing down, which it appears to be, it means the first quarter turn, see, the whole thing was 3.96 seconds, but this is going to what? Be 1/4 of that? No, this is going to happen in a shorter time. That's going to be a little longer if we divide this into 4 parts, and the longest time is going to be this as it comes to a stop. So that's how the motion looks. It starts out and slows down, slows down, slows down. So it starts at its highest velocity and gets less and less. Okay, here's the last one. You should read it over. A boy on a merry-go-round. A girl gives the merry-go-round a push for 0.2 of a second, and then lets go. So what are we going to expect? We're going to expect the thing to accelerate for the first 0.2 of a second, and then go around perhaps at a constant speed, assuming the merry-go-round is frictionless. Let's take a look. Yeah, see? You can see the acceleration, and now it's going around. Yeah, it looks like it's a steady speed. We can check that by measuring at different points to see if it covers the same distance in the same time. But it looks pretty constant. So this has 2 parts. This is a new idea. It has the accelerated part and the part that isn't accelerated. So you can't just take that 8 seconds and divide it into the turns. That will give you an average over the whole thing, but there's 2 parts, so you don't want to do that. You got to deal with the 2 parts separately. The first 0.2 of a second is an accelerated motion. You deal with that. And the time from 0.2 of a second to the end is the part where the velocity is constant, or at least it appears to be. Okay, if you have any remaining questions, email me.